Good evening to everybody. I'm Gaetano Pavone, researcher at Polytechnic University of Bari. With my research team composed of Aguinaldo Fraddosio, Andrea Micheletti, and Daniele Piccioni, I will talk about analysis of novel adaptable expanded Tensegrity tower. The present work explored the capabilities of such system to cable-driven shape-changing structures. Adaptive Tensegrity structure have been considered for space applications, deployable grids, folding system, innovative antennas, and Tensegrity robots, for example. In this study, shape changes of tensegrity structure are obtained by using active and passive cables. The module of the tower is composed of 8 struts forming two sets of 4 equal length compressed elements and connected by a vertical cable, 4 horizontal bottom and 4 horizontal top cables, and 8 diagonal cables. The modular tower analysis is composed of 2 modules sharing 4 horizontal cables and has 4 independent self-stress states and no mechanisms. It can be noted that the elementary tensegrity cell, as well as the tensegrity tower, are stable but not superstable tensegrity system. That is stable irrespective of the level of the self-stress and material properties of the elements. From the analysis of the symmetry cable orbits, 4 groups of symmetry elements can be recognized. Thus, 12 possible combinations can be realized for the analyzed tensegrity tower. The actuation process of the tensegrity structure is allowed by appropriate choices of active and passive cables. The choice of the different types of cable is governed by symmetry edge orbits, that is, cables in symmetric position can be collected in the same group. First, initial symmetric self-stress stable configuration can be obtained by applying initial polystyrene and symmetrically placed passive cable. Then, the actuation process starts. For example, by actuating the vertical cables of 70% of their initial length and by considering diagonal cables as passive element, it is possible to obtain a stretched configuration of the tower. However, for complex tensegrity towers there can be considered several groups, and the number of possible combinations increases with them. Thus, a key problem is to find an efficient strategy for predicting the qualitative response of the structure and for preliminarily evaluating the best choice of active and passive cables, without performing complex nonlinear analysis. The proposed strategy is based on the evaluation of the linear mechanical behavior of the structure in the neighbor of the self-stress configuration by simulating very small values of the cable actuation length. Calculations can be carried out by considering the virtual work principle applied in 2 different steps. In the first step, the actual self-stress structure is considered as the kinematically compatible system as well as statically equilibrated system. Thus, it is possible to write the following equation that can be simplified taking into account the symmetry properties of the structure. Moreover, since the elongation of the ordinary cables as well as of the strut in the self-stress states is negligible with respect to the elongation of active and passive cables, the lattice equation can be rewritten as follows, and thus the unknown elongation of passive cables can be obtained by solving the equation. In the second step, we consider the actual self-stress structure as the kinematically compatible system and a suitable loaded system as a statically equilibrated system. For our purpose, the non-null elements of the external load vector are equal to unitary upward and downward forces applied to the top and bottom nodes respectively, which are opportunity constraints for removing the rigid body motion. In the virtual internal work, the internal forces of the statically equilibrated system can be obtained by considering the inverse generalized of the equilibrium matrix. In the virtual external work, left side of the equation, each upper node contributes equally to it. Hence, it is possible to obtain the vertical displacement on upper nodes as follows. In synthesis, the strategy for predicting the qualitative response of the structure can be summarized in the following steps. In particular, the ratio between the displacement of a single upper node and the work done by active cable, normalized to the maximum value obtained among all the considered passive-active group combinations, can be used as a scalar parameter for evaluating the efficiency of a single choice of active and passive cables. Now, our strategy is compared with the nonlinear response of the tower for a very small cable actuation length of the active cables equal to 1%. It can be observed that the estimated error related to elongations of passive cable is negligible in both shape changes. By performing the analysis according to the proposed strategy, it emerged that the maximal vertical displacement, as well as the maximum efficiency, can be obtained in the highlighted cases. For avoiding overlapping of the elements, large cable actuation lengths are not considered. Thus, for our purpose, we perform the nonlinear analysis according to an actuation length equal to 10%. As it can be noted, the procedure allows predicting the best choice of active and passive cables in terms of maximum vertical displacements of the upper nodes for stretching and shrinking shape changes, as well as in terms of maximum efficiency in shrinking. Furthermore, as it can be expected due to the symmetry of the structure, the actuation of the shared horizontal cables with base and top cables as passive element, as well as exchanging them, leads to numerically null vertical displacement of the upper nodes. This circumstance suggests that these particular choices cause a very small change in the height of the tower when considering large elongation in the nonlinear regime. Notably, by exchanging active with passive cables, it is obtained a reverse shape change of the structure. Moreover, the trend of the performance of a choice in terms of vertical displacement is preserved if active and passive cables are inverted. In conclusion, preliminary analysis of shape change of novel adaptable expanded tensegrity tower have been performed by means of cable actuation. Two different kinds of shape change have been considered in this case. The actuation process of the tensegrity structure is provided by appropriate choices of active and passive cables. Different groups of cables are defined according to their symmetry properties. An effective strategy for preliminary evaluating the best choice of active and passive cables without performing complex nonlinear analysis of the cable actuation process has been presented. And finally, further numerical and experimental analysis will be conducted to investigate the influence of the geometrical and material parameters on the shape change capabilities of the tensegrity towers. Thank you for your attention.